Okay. Right. So today we're going to be talking about things involving the fundamental theorem of calculus. So there's two parts to the fundamental theorem of calculus, and we'll probably end up just needing both parts. So I may as well just introduce both parts now. Yeah. So FTC, the first part of it is involves what happens when you take the derivative of an integral. So it looks like this: d dt of something from a to x of f of x dx. Well, actually, usually we like to put the oh yeah, no, usually we don't write it like this. We usually put the x outside, and the t is the variable inside. So let me fix that. Okay. And there is a slight reason for it. It's because this integral, you kind of think of it as a new function, capital F of x, and something you're taking the derivative with respect to the new variable x. What the fundamental theorem of calculus says is that this is equal to just f of x. So in this way, it's like that the derivative and the integral will cancel each other out. So if you take the derivative of an integral, that cancels out and gives you back the original function, except for the fact that you are substituting the variable out, replacing it. But one thing that can happen, and most likely we will see this. Yeah, we do see that in the number 2 of the homework is what if this limit is not just x, but is some function. So integral from a to, let's say, g of x, f of t dt. And well, what happens is that this is technically a chain rule. You could actually play around with the symbols and figure out that this integral is actually capital F of g of x. And so then what this ends up becoming is f of g of x times g prime of x. So you can really view this as being a chain rule, where what we've done is we substitute in the g of x into the function, replacing out that variable t, but then we also have a chain rule component tacked on at the end. And so this is just a generalized version of number 1. That's the way you should think about it. So that's the first half of fundamental theorem of calculus. The second half is actually I don't have this written, but it's a way to think about this. I guess I don't need the t in this case, so I'll need just fx dx. So and this is really the way that we tell you how to actually evaluate these definite integrals. So the idea is that you find the antiderivative, and then you evaluate from a and b, you subtract the two. So you do f of b minus f of a. This is just a notational shorthand. And the way to actually see that this has anything to do with a derivative and an integral is actually to notice that this thing inside is actually I guess you could say t of f of capital F of t. So if you sort of recast this in terms of that, this is capital F of t, then you can see that like it's the integral of a derivative of a function this time around. So these two are kind of like saying like what happens if you're taking the derivative of an integral, what happens if you're taking the integral of a derivative. That's kind of what FTC is about. but really 2 is used everywhere for when you're evaluating an integral. Because normally, like in previous homework, we were showing you how to calculate these definite integrals by thinking about them geometrically as areas under curves and doing like a summation. Well, the technical definition of integral uses the Riemann sum idea, limit of a sum of rectangles, and that's just really irritating to work with. So FTC part 2 is actually the typical way that we do these kinds of calculations. Is instead we find the antiderivative and then we just do a evaluation on it. Right? It definitely beats out having to compute a sum, and especially because you guys don't even touch upon how you actually make a sum converge, an infinite sum converge. That's something that you see more of when you actually get to Calc 2. Okay, and I guess that's everything I want to say about material. So I guess, are there any questions? If not, then we'll get started on the problem set. So, yeah. All right. Okay, so let's get going on this. Right. So number 1 has 4 parts or 5 parts, and we're just doing a bunch of these things, these definite integrals as they're called. So this all just requires FTC part 2. Find the antiderivative and then evaluate. So for the first one, you should definitely see that this is 5 ln absolute value of x plus x squared over 2. So I don't know. I think that's pretty straightforward to just be able to see that right away. And then you evaluate. So if I plug in e, I'm going to get 5 times 1. So that's 5 plus e squared over 2. And then I have to subtract off what I would get when I plug in 1. So I'm just going to open a big set of parentheses and then evaluate at 1. So when I plug in 1, I'm going to get 0. I'm just going to write that there to keep track of what I'm doing. And then a half. Okay. So this is 5 plus e squared minus 1 over 2. Oh, wait, no. Actually, there's a better way to combine this. I see. Why did I not see that just now? There's a better way to combine that. So 5 minus a half, that's 9 halves. Computer's being a bit frozen. How strange. Okay, well. Oh. 9 halves plus e squared over 2 is the better way to write that. Okay. Well, for part B, you just integrate cosine and sine. So integrating cosine is the easy one. That just becomes sine. Integrating sine, it's actually nice to keep the negative into account because normally when you integrate sine, you're going to end up with negative cosine. So if I just integrate negative sine, I see that that whole thing is going to become cosine. And then I have to evaluate from 0 to pi. Okay, well, one of these terms actually is going to be 0 for everything. But let's just think about this. Evaluating pi first and 0. So evaluating pi, sine is going to become 0. Cosine is going to become -1. And then you subtract off the evaluation at 0. If you plug in 0, the sine is 0, the cosine is 1, so you get +3. So you get 0 plus 3. Okay, and so this in total is -6. Right. For C, well, it's nice to rewrite this as a power, an exponent. So -1/2. So then when we integrate this, reverse power rules. So it's going to be 5x to the 1/2, and then divided by 1/2, which is the same as multiplying by 2. And then we would have a +7x. And we will have to evaluate this from 4 to 81. Okay, well, that's a bit annoying. So this is 10. We've got 9 here, so 90 plus 81 times 7 minus 20 plus 7 times 4, 70 plus 81 minus 7. I mean, you could calculate this by head, I guess is what oh, not 7 times 4. Yeah, I'm trying to calculate this by hand, but I don't want to. So instead, I'll just look at what this is actually going to give you. Oh, come on. So what this is actually going to give you is 609. Okay. Okay. And all right, so for D, if you pull the 4 out, then what you have inside the integral is something that you should immediately recognize. Well, hopefully, if you have enough practice, you'll immediately recognize it's arctangent, right? The integral of that function is arctangent. And so you'd write something like that, evaluate from -1 to 1. And so then the only tricky thing is how do you actually evaluate arctangent? I'll say what I just did here. So what I just did just now is I'm denoting that I want my evaluation to only apply to the arctangent function. I don't want to, or I'm pulling the 4 out and just like saying I'm gonna multiply that by everything that I get from the evaluation. It's just a factoring that I did. Okay, so yeah, arctangent. So tan inverse of 1, you have to recognize that this is saying the same thing as tangent of what angle is going to give you the value 1. And so that the answer to that is pi over 4, 45-degree angle. Pi over 4 will give you that value. And you can also consider what happens with the -1. And so that's asking when is tangent going to give you a -1, and to consider only the well, to consider the correct quadrant. So the way that the inverse tangent function restricts, it only involves these 2 quadrants. So for evaluating at -1, and we have to subtract, we'll end up with a -1/4. So we end up with pi over 2, so then we end up with 2 pi. When we calculate that out, that doesn't look like a pi. But my stylus is being a bit weird. What is it doing? All right. Maybe I can close something. Yeah, okay. Maybe that'll run a bit better. Okay. Right. Any questions so far? Just want to make sure I'm not going too fast. Okay. So this reverse power rule. So we add 1 to this power, and then we would divide. So adding 1 to this power is going to give you 1/3. And then you're going to divide by 1/3, which is the same thing as reciprocated. You multiply by 3. And this one, this is z to the 1/3 power. So if you add 1 to that, you get z to the 4/3. Reciprocate that, you get 3/4 for multiplying. And so it cancels. And now you want to evaluate this whole thing from 1 to 64. Right, so now we have to consider what is the cube root of 64. And you hope that 4 is going to do the trick. So yeah, it does actually work out. And so yeah, for this one, you get 3 times 4. I can just write that as 12. Plus 3 times. All right, and so here I actually have to raise 4 to the 4th power. That's multiplying this by 4, so 128, 256. And then you subtract off, evaluating this at 1. Well, okay, that's not so bad. 3 plus 3. Yeah. Okay, great. And well, there's a bit of arithmetic to that. I'm just going to skip the arithmetic and write down the answer. Right. Okay, so that's how you deal with these definite integrals and using FTC part 2. Number 2's problems all involve FTC part 1. So we're sort of switching gears in this case. And we're now dealing with the derivative of an integral. So the thing about this, this is always going to give you a function. And yeah, usually what we do is we just plug directly in. So for A, everything is as straightforward as can be. All you do is you replace the t with x, because that's what the thing is in terms of. That's it. For B, there's actually something else going on. It's important that with these problems, it's important that the number is on the bottom and the variable is on the top. So what we have here is the reverse of that, right? Variables on the bottom. So what you want to do is imagine that you are flipping the order of integration. And you know that when you flip the order of integration, you're actually introducing a negative to the answer. So if we wanted to justify this completely, I would have to write a couple things, but like pretend that this is not something that you normally would write, I would say. Just I'm writing it just to illustrate what I'm saying in words. Oh, T. So yeah, I've flipped the order of integration, and doing that introduces a negative. And then from that point, you just apply FTC part 1 as you normally would. So derivative of an integral, imagine you pull that negative out, so you have the derivative and integral right next to each other. Yeah, and then doing those two things in succession, what it does is it replaces out the variable. And so you end up with the negative of part A. Right, and now C is quite different. So in this case, what you have is something with 2 variables, right? With a varying lower limit and upper limit. And the thing about that is, well, that doesn't exactly match. So we have to do something. We have to kind of modify our integral in order to be able to work with it. And the usual thing you would do is you'd split that integral into 2 parts. You'd split it to be the part from the lower limit to some constant, some number. And the easiest number to pick is 0. So pretty much just pick 0. And so you have something like this. You're going to split the integral into a part that goes from the lower limit to 0, and then from 0 to the upper limit. And so, yeah, you can imagine doing that. And then you now have 2 integrals that you can then just take the derivative of using FTC part 1. So for the first one, you're going to have to put that negative. And here we also actually are introducing the chain rule part, the generalized aspect of the FTC part 1. So here, we're replacing t with 7x for the first integral. So that's going to be 7x sine of 7x. But then because of the chain rule that we need to tack on, we need to take the derivative of 7x, which is 7. And so that's the first half of the integral. The second half is going to be taking the derivative of this integral from 0 to x squared. And so what we need to do, well, we plug in, but then we have to multiply by the derivative. So that's the whole thing. One important thing to notice is I'm actually not putting this plus c that we have been mentioning previously. That's actually an important consideration. Like, so you only put plus c for indefinite integrals. So that means that you have an integral without any limits. So in particular, it does not apply here because notice also like the last thing you're doing here is you're taking a derivative. That derivative is actually going to kill off any constant that you would normally get. But then also in the first place, you kind of don't have a constant because with these definite integrals, you don't have a constant since it's like you end up subtracting off the constant that you would normally get. Not sure if that completely makes sense, but okay. Are we okay so far? Everyone following along? 2 thumbs up. All right, good, good. 21 minutes left. Let's see how much time. I think we can do one more page. Yeah. All right. So, so number 3 all has to do with this graph, but I think it kind of interprets things just differently each time. All right, so notice A is a function that we construct out of some velocity function. Okay, that's fine. And it's just integrating, so just think of it as an area. That's why we're using the letter A. Okay. A of 0. Notice what happens if I plug in 0. I'm going to get an integral from 0 to 0. By definition, that's 0. Like it's sort of like you're trying to take the area of something that has like 0 width. So it makes no sense. What if I plug in -1? So then that becomes an integral from 0 to -1. Well, that's going backwards. Okay, so it's going to be the negative of whatever the signed area would be normally. And we see that it would be this part that I'm pointing at. So it's going to be the negative of that. Okay, so that we just view that positively. And so that's 1/2 times 1 times 4. And so that's just 2. Okay. What about A of 2? So if I plug 2 into this integral, that's the same as taking the area or just visualizing the integral from 0 to 2 here. And you see that these two triangles are going to cancel out completely. So that's just going to be 0. Don't think you really need to say any work on that. Yeah. And then from 0 to 4, well, that just continues on from that. So we know that going from 0 to 2, the integral is 0. So I just need to consider 2 to 4. And that's the triangle. So I can think about the area, 1/2 times 4 times 2, which is going to give me 4. So that's part A. Now part B, notice now, this is asking about the derivative and then plugging in. So the derivative, we can do some work. We can write some things. So we should start with like a prime of x. And the thing is that a prime of x, that's d dx of this integral. Which is exactly the format for FTC part 1. And so we know that the derivative and integral will cancel each other. We get v of x. So a prime of x is the function v of x. And so you just now plug in 2. So a prime of 2, or yeah, v of 2. And so now we can just look at the graph and see what that gives us. That gives us 4. Okay. C. All right. So when is it increasing and when is it decreasing? So that's interesting, right? Increasing and decreasing. The thing is that those are actually statements about the derivative. So in disguise, what this is saying is to like, the idea is that we should be thinking about the derivative, which means we should be thinking about the v of x, since the derivative of the a function is the v function. And so when is it increasing? Remember that that means the derivative is positive. Well, if v is the derivative, then this is saying when is the function positive? When is the function v positive? So increasing corresponds to, well, maybe I'll write what I just said. I'll write that down. So this is the same. It's not just implies. It's equivalent. So maybe I'll use that symbol to represent that. So it's saying that v of x is positive, right? Which is from minus infinity. Some really keeps getting louder. Minus infinity to minus 1, and from 1 to 4. Now, when is it decreasing? That's the same thing as saying when is v of x less than 0, and that should just be the complement. So minus 1 to 1, union 4 to infinity. I can check that that is indeed when the graph of the function is negative. Okay. Well, now for D, suppose that S is the position, suppose that S prime is V. So that's really saying that S is kind of just this A function that we've been working with. But all right, let's see. S of 0 is 5. Find the position of the particle at time 4 seconds. How do I want to explain this? Well, the idea is to use the second part of FTC, where it involves this integral from 0 to 4. So the integral 0 to 4 of v of t dt, that's going to, so we know that the antiderivative of the v function is going to be the s function. And so this definite integral is going to be the same as subtracting s of 4 from s of 0, right? And that's actually going to calculate for us the position. So we know what s of 0 is. We know it's 5 feet. When we calculate this, we're going to end up getting the difference. So we'll be able to calculate what s of 4 is, which is going to be the position of the particle that the problem is asking us for. So then we can go ahead and the way we calculate this definite integral is we look at it, or we notice that this is actually something we already calculated. This integral from 0 to 4 is simply this a of 4, which is just 4. And so in sum, this is saying s of 4 minus 5 is equal to 4. And so then s of 4 is equal to 9. And we should tack units on at the end, so 9 feet. It's probably best if I stop here, because otherwise there'll be too little to talk about next time. But are there any questions? If there aren't any questions, then I'll see you guys next time.